Alright, some applications of circular motion. We consider the conical pendulum, which is like this. Basically, it involves a pendulum moving in a horizontal circle. The forces acting on that pendulum bob mass, obviously the weight force mg, always vertically straight down, and the tension force along the string usually that is supporting the mass, and that's normally at some sort of angle greater than 0 from the vertical line. The resultant of these two forces provides the centripetal force in this case. This resultant can be calculated by taking components of the tension force and then considering the vertical component and the horizontal component. We might ask these questions: which component provides the centripetal force, and which component equals the magnitude of the weight force? Now, if you examine this diagram, it's fairly obvious that t cos theta is the vertical component that must be equal and opposite to the weight force mg, leaving t sin theta, the horizontal component, to give us the centripetal acceleration. So that must be the magnitude of the centripetal force. Example, if we attach a mass of 200 grams, the string length 80 centimeters, and it's swung as a conical pendulum, making a horizontal circle of diameter 42 centimeters. Now that immediately should be halved to make a radius 21 centimeters, because that's going to be the important value you use. A. Calculate the tension in the string and the centripetal force acting on the mass. So to do this, we need to consider the following. To get to the tension force, we can use mg equals t cos theta. But in order to use that equation, we need to find theta, of course. And we find theta using the 21 centimeters and the 80 centimeters and a bit of trigonometry. So there's the bit of trigonometry I was talking about. Once you've got the angle, you can then use mg equals t cos theta, rearrange so you have mg divided by cos theta, and you should find the tension force. Then, to find the centripetal force, you can use the other equation for the other component, t sin theta, because that of course will be the magnitude of the centripetal force. Part B, what is the angular velocity and period for the circular motion of the mass? Well, to find the angular velocity omega, we know the centripetal force, and we also know that the two are related by the equation centripetal force Fc equals m r omega squared. So there we can rearrange and find the angular velocity omega. The period, well, we know the period is related to the omega, the angular velocity, by 2 pi divided by omega equals the period capital T. So once you've had a go, check your answer. They should be the following. Period T, sorry, the tension T should be 2.03 newtons, and the centripetal force 0.532, angular velocity 3.55 radians per second, and the period T 1.77 seconds in the end. Right, now for bank curves, another application of circular motion. We can consider a car moving around a horizontal circle on a banked curve. The banked curve will be banked at an angle theta. The two forces acting on the car will be the weight force mg and the reaction force perpendicular to the surface of the road acting through the tyres, and we'll call that small n. the components of N are the things to look at, in a similar way to what we just saw with the components of tension for a conical pendulum. We can resolve the vertical component, which must be equal and opposite to the weight force. That's N cos theta. And the horizontal component again will give us the centripetal force, and this time it will be N sine theta equaling the centripetal force. Okay, so we can use those two component equations to derive an expression that is useful to find out the maximum velocity a car is able to travel around a particular bend of a given radius of curvature and camber, which is the word that means angle of banking. How? Well, we take the two component equations. There's the horizontal one, which we manipulate a little bit to bring in the mv squared upon r for the right hand side, and we combine that with the vertical equation, n cos theta equals mg, by dividing them into each other as follows. So you have n sine theta over n cos theta, which equals tan theta. The n's cancel out, and the trig identity sine theta over cos theta is replaced with tan theta. The right hand side simplifies down, the masses cancel out, and we are left with this expression involving the maximum velocity possible in terms of the angle of the banking and the radius of curvature r. Okay, we're looking at vertical circles now. Now, for an object that's swung in a circle that vertically, you have to be careful about the vector sums of Fc and the weight force when you're trying to work out things like the tension force. If we consider this point at the bottom here, we know that if it's a string holding a mass that's being swung vertically, the tension force at this point must be straight up, and the weight force, of course, is straight down. I can just squeeze that in. Oops, that's mg. The centripetal force, we know, of course, is the resultant of these two, must be acting straight towards the centre of the circle. So we could say that the centripetal force in this case would be equal to the tension force, take away the weight force mg. However, at the top we have to be careful because things change. The tension forces, of course, are downwards again, but will be much less than it was before at the bottom, and that's because the weight force is still straight down, and the sum of those two things this time must be equal to the centripetal force, the net force acting towards the centre of the circle. So it depends where you are as to which of these two equations you use. Things are more complicated at the side of the circle. For that, we'll leave that for another time. Okay, here's an example of a vertical circle question to do with a roller coaster ride called the Loopy Opie Opie. We're told that the time it takes for one complete revolution is 4 seconds. So in order to find the angular velocity, we can simply use omega equals 2 pi over the period capital T. So that's 2 pi over 4 seconds, which should give us 1.57 radians per second. For part B, we use the equation V equals R omega and multiply the 1.57 by 10 meters, which is the radius. So we get, what, 15.7 meters per second for the velocity. For part C, the force exerted by the structure on the person, that's equivalent to the tension force of the string on the mass in the previous slide. At the bottom of the circle, of course, we are subtracting the tension force from the weight force to find the centripetal force. In this case, we're trying to find essentially the tension force So we need to add the centripetal force and the weight force. A quick calculation involving mv squared over r will give us Fc, of course. So I'll just show that here. This is the equation we use to find that. Plug all the numbers in, you should be getting 1725 newtons, and for mg you should be getting 9.81 times the 70 kg is 686 newtons. If you add those two numbers together, you will find the tension force at the bottom, part 1. If you subtract those two numbers, you'll find the force on the person at the top of the circle. Halfway up, we need to use trigonometry. So here's the situation halfway up. Now we can draw in the centripetal force Fc. It will be the same value as it always ever was. We'll call that Fc. Now the other important quantity, of course, is the weight force, which is always straight down, and we'll add that in this position here. You'll see why soon, because of course the weight force must be added head to tail with the tension force, or the force that the roller coaster exerts on the person at this point here. That position there, of course, the structure is pushing basically along this line here, so slightly upwards, assuming a rotation around this way, slightly upwards and of course inwards, so that the component horizontal is giving us the centripetal force still, and when you add that vector to this mg vector, you get the resultant as the centripetal force Fc. The other important idea, of course, is that this is a 90-degree angle, and hence we can use trigonometry to find the actual value for the tension force, or the force the structure exerts on the person. And a quick calculation on my calculator, squaring Fc, squaring mg, adding them and then square rooting gives me 1856 newtons for the force, tension force in this case.